Tribology is the science and engineering of interacting surfaces in relative motion. It includes the study and application of the principles of friction, lubrication and wear. Tribology is a branch of mechanical engineering and material science. Etymology. The word tribology derives from the Greek root tau rho iota beta of the verb tau rho iota beta omega, tribo, I rub, in Classic Greek, and the suffix logi from lambda omicron gamma iota alpha. Logia, study of, knowledge of. It was coined by the British physicist David Tabor, and also by Peter Jost in 1964, a lubrication expert who noticed the problems with increasing friction on machines, and started the new discipline of tribology. Fundamentals. The tribological interactions of a solid surface's exposed face with interfacing materials and environment may result in loss of material from the surface. The process leading to loss of material is known as wear. Major types of wear include abrasion, friction, erosion, and corrosion. Wear can be minimized by modifying the surface properties of solids by one or more surface engineering processes or by use of lubricants. Estimated direct and consequential annual loss to industries in the USA due to wear is approximately 1 to 2% of GDP. Engineered surfaces extend the working life of both original and recycled and resurfaced equipment, thus saving large sums of money and leading to conservation of material, energy and the environment. Methodologies to minimize wear include systematic approaches to diagnose the wear and to prescribe appropriate solutions. Important methods include point-like contact theory was established by Heinrich Hertz in 1880s. Fluid lubrication dynamics was established by Arnold Johannes Sommerfeld in 1900s. Technology, where multidisciplinary engineering and management techniques are used to protect equipment and machinery from degradation. Horst Ziecho's systems approach, where appropriate material is selected by checking properties against tribological requirements under operating environment. Asset management by material prognosis, a concept similar to technology which has been introduced by the U.S. military for upkeep of equipment in good health and start-ready condition for 24 hours. Good health monitoring systems combined with appropriate remedies at maintenance and repair stages have led to improved performance, reliability and extended life cycle of the assets, such as advanced military hardware and civil aircraft. In recent years, micro and nanotribology have been gaining ground. Frictional interactions in microscopically small components are becoming increasingly important for the development of new products in electronics, life sciences, chemistry, sensors and by extension for all modern technology. Friction regimes for sliding lubricated surfaces have been broadly categorized into, on the basis of the Staib X curve. These curves clearly show the minimum value of friction as the demarcation between full fluid film lubrication and some solid asperity interactions. Staib X and others systematically studied the variation of friction between two liquid lubricated surfaces as a function of a dimensionless lubrication parameter eta n, p, where eta is the dynamic viscosity, n the speed and p the load projected onto the geometrical surface. The Staib X curve has been a classic teaching element in tribology classes. History. Duncan Dowson surveyed the history of tribology in his book, History of Tribology. This comprehensive book covers developments from prehistory through early civilizations and finally the key developments up to the end of the 20th century. Historically, Leonardo da Vinci was the first to enunciate two laws of friction. According to da Vinci, the frictional resistance was the same for two different objects of the same weight but making contacts over different widths and lengths. He also observed that the force needed to overcome friction doubles when the weight doubles. Da Vinci's findings remained unpublished in his notebooks. Guillaume Montans rediscovered the classic rules. They were further developed by Charles Augustin de Coulomb. Charles Hatchett carried out the first reliable test on frictional wear using a simple reciprocating machine to evaluate wear on gold coins. He found that, compared to self-mated coins, coins with grits between them wore at a faster rate. Staib X curve. The Staib X curve, or Staib X curve, which is used to categorize the friction properties between two surfaces, was developed in the first half of the 20th century. The research of Professor Richard Staib X was performed in Berlin at the Royal Prussian Technical Testing Institute. Similar work was previously performed around 1885 by Professor Adolf Martens at the same institute, and in the mid-1870s by Dr. Robert H. Thurston at the Stevens Institute of Technology in the U.S. Professor Dr. Thurston was therefore close to establishing the Staib X curve, but he presented no Staib X-like graphs, as he evidently did not fully believe in the relevance of this dependency. Since that time, the Staib X curve has been a classic teaching element in tribology classes. The graphs of friction force reported by Staib X stem from a carefully conducted, wide-ranging series of experiments on journal bearings. Staib X systematically studied the variation of friction between two liquid lubricated surfaces. His results were presented on 5 December 1901 during a public session of the Railway Society and published on 6 September 1902. They clearly showed the minimum value of friction as the demarcation between full fluid film lubrication and some solid asperity interactions. Staib X studied different bearing materials and aspect ratios d/L from 1 to 1 to 1 to 2. The maximum sliding speed was 4 meters per second and the geometrical contact pressure was limited to 5 megapascals. The reason why the form of the friction curve for liquid lubricated surfaces was later attributed to Staib X. Although both Thurston and Martens achieved their results considerably earlier, maybe because Staib X published in the most important technical journal in Germany at that time, Zeitschrift des Vereinsdeutschen Ingenieur, Martens published his results only in the official journal of the Royal Prussian Technical Testing Institute, which has now become BAM, the VDI journal, as one of the most important journals for engineers. Provided wide access to these data, and later colleagues rationalized the results into the three classical friction regimes. Thurston, however, did not have the experimental means to record a continuous graph of the coefficient of friction, but only measured the friction at discrete points. This may be the reason why the minimum in the coefficient of friction was not discovered by him. Instead, Thurston's data did not indicate such a pronounced minimum of friction for a liquid lubricated journal bearing as was demonstrated by the graphs of Martens and Staib X. Just report. The term tribology became widely used following the Just report in 1966. The report said that friction, wear and corrosion were costing the UK huge sums of money every year. As a result, the UK set up several national centres for tribology. Since then the term has diffused into the international engineering field, with many specialists now claiming to be tribologists. There are now numerous national and international societies, such as the Society for Tribologists and Lubrication Engineers in the USA. The Institution of Mechanical Engineers Tribology Group in the UK, or the German Society for Tribology and MYTRIBOS. Most technical universities have researchers working on tribology, often as part of mechanical engineering departments. The limitations in tribological interactions are, however, no longer mainly determined by mechanical designs, but by material limitations. So the discipline of tribology now counts at least as many materials engineers, physicists and chemists as it does mechanical engineers. New areas of tribology. Since the 1990s, new areas of tribology have emerged, including the nanotribology, biotribology, and green tribology. These interdisciplinary areas study the friction, wear and lubrication at a nanoscale, in biomedical applications. and ecological aspects of friction, lubrication and wear. Applications. The study of tribology is commonly applied in bearing design but extends into almost all other aspects of modern technology, even to such unlikely areas as hair conditioners and cosmetics such as lipstick, powders and lip gloss. Any product where one material slides or rubs over another is affected by complex tribological interactions, whether lubricated like hip implants and other artificial prostheses, or unlubricated as in high-temperature sliding wear in which conventional lubricants cannot be used but in which the formation of compacted oxide layer glazes have been observed to protect against wear. Tribology plays an important role in manufacturing. In metal forming operations, friction increases tool wear and the power required to work a piece. This results in increased costs due to more frequent tool replacement, loss of tolerance as tool dimensions shift, and greater force is required to shape a piece. The use of lubricants which minimize direct surface contact reduces tool wear and power requirements. Bibliography. Surface wear, analysis, treatment, and prevention. R. Chattopadhyay, published by ASM International, Materials Park, O. 2001, ISBN 0-87170-702-0. Advanced Thermally Assisted Surface Engineering Processes. Ramnarajan Chattopadhyay, Kluwer Academic Publishers, M.A. 2004. DeGarmo, Paul, J.T. Black, and Ronald A. Koza. Materials and Processes in Manufacturing. Upper Saddle River, New Jersey. Prentice Hall, 1997. ISBN 0-02-328621-0. Zumgar, Karl-Heinz. Microstructure and Wear of Materials. Tribology Series 10. Elsevier. ISBN 0-444-42754-6. Heshmat, Hushang. Tribology of Interface Layers. CRC Press. ISBN 978-0-8247-5832-5. Lit. Fred. Starting from Scratch. Tribology Basics Volume 1. STLE. Retrieved 10 June 2010.